So today we're going to talk about what you do when the number underneath the square root symbol is not a perfect square. Okay, so we know that when we take the square root of a perfect square, the answer is an integer. We know that the square root of 25 is 5, square root of 36 is 6. Something we really haven't talked about is this idea that when you square a positive number, it is positive, right? This is positive 16. 4 squared is 16. But when you square a negative number, like negative 4, it's also positive 16. Both of them are positive perfect squares, even though you started out with a negative number or a positive number. You don't know what you might have squared to get positive 16. So this becomes very tricky when you're going backwards, when you're taking a square root. How do we know which answer to give, right? The square root of 16, the way that it's written here, I could have squared 4, or I could have squared negative 4 to get 16. So is my answer positive 4 or negative 4? So in mathematics, we have assumed that when you see this symbol of the square root of 16 like that, you should assume that it's the positive answer. You're going to always assume that. Later on in algebra, like a year or so, you're going to learn some things about doing plus or minus. But right now, when you see a square root symbol like that, you can assume that it's the positive square root. So some examples of perfect squares like this. If you just had this problem, the square root of 64, you would say that it's 8. The square root of 100 is 10 times 10, which is 10, right? The square root of 100 is 10. Square root of 25, which we can also rewrite 25 is 5 times 5 underneath the radical. These are equivalent expressions, right? 25 and 5 times 5 are the same thing. And that is 5. Square root of 5 times 5 is 5. So looking for a perfect square underneath the radical. Okay, so back to the original question, which is, what if it's not a perfect square? What if the number that we have is not a perfect square? So here's an example, square root of 50. So the thing is you have to try and find a perfect square factor of the number under the radical. So if we did like a factor tree for 50, we would see that 5 squared times 2 is 50. And there's your perfect square right there, 5 squared. So if there is a perfect square underneath the radical, there is something that you can do, and we'll see what you do next. So now the question is, what do you do when you have the square root of a number that's not a perfect square, like the square root of 50, right? We need to write it as the product of a perfect square times the other factor. So in the case of 50, it was 25 times 2, right? And 25 was a perfect square factor of 50. So it was easy to write 50 as the product of 25 times 2 with a perfect square as one of the factors. So what we can do next is we're able to actually write radicals or square roots that have a product underneath, like 25 times 2. We can split it into 2 different radicals. So the square root of 25 times 2 actually becomes the product of the square root of 25 times the square root of 2. And I'm leaving the 25 in the perfect square now just to show you what actually happens. So the square root of 25 becomes 5. But the square root of 2 is not a perfect square. We have to just leave it underneath the radical. There's nothing else you can do with that. So you have to just leave it under the radical, and you just say it's 5 times the square root of 2. Let's try one more example to see if it makes sense. So what about the square root of 32? We know that 32 is not a perfect square, right? So first thing that you want to do is find a perfect square factor of 32. And we know that 32 equals 16 times 2. And 16 is a perfect square, right? You could do it with a factor tree if you want to, but you don't have to if it's pretty obvious what the perfect square factor is. But that might take a little practice to actually see what it is. So I'm going to write the square root of 32 as 16 times 2. And what we did last time was we said the square root of 16, right, because 16 was the perfect square. So I could then write the square root of 16 times the square root of 2, and 2 is not a perfect square. So this part becomes 4, and this part remains underneath the radical, and it's 4 times the square root of 2. If there's no times there, its multiplication is implied. Okay? Let me know if you have any questions. Oh, just one more question I wanted to add. This is kind of like a challenge. I'm curious if you think that these numbers, 3 times root 11 and 5 times root 3, are they irrational or rational? It's a really important question.